get ready, Venn diagrams. Cool, today we are talking about Venn diagrams. In this paragraph, we will see the notion of this image here, this diagram, which we call a Venn diagram, which consists of a universal set, U, like we've seen in questions, universal set means the world of a particular question. When they give you, say, for example, a set of numbers or something like that, that would be your U, and we indicate that, we show that, demonstrate that using a rectangle. That's our U. Now, inside this U, we put little circles, and those circles will represent other sets given within the particular problem. For example, let's say that the universal set U is all of the x's such that the x's are less than or equal to 10, and also x's are positive integers. Remember this little Greek letter epsilon, it means that this is an element of. This z means whole numbers. It comes from the German word Zahlen, which means number, and this plus means positive. So specifically, this set really means the numbers between 1 and 10. They just gave it in a strange way, hoping you would get it wrong, but little did they know about you. You will not fall into any traps. So here, 1, 2, 3, 4, 5, all the way up to 10 would be your set, U. Now, they also give you this set here, S, which is the set of numbers 2, 4, 6, and 7. Well, easy peasy. Let's go ahead and draw a Venn diagram here. And now we're going to put all of these numbers in there, 1, 2, 3, 4, 5, all the way up to 10. But the numbers 2, 4, 6, 7 need to be in a circle, which we will label as S. So you see here in the center, we draw a little circle. Please make sure it's perfect, because I'm OCD. If I don't see a perfect circle, you get disqualified. I'm joking. This is the circle S. Inside the circle, you put 2, 4, 6, 7. 2, 4, 6, 7, done. Outside the circle, you put the rest of the numbers in your universal set. So in this mini universe of numbers 1 to 10, all that's left is 1, 3, 5, 9, 8, and 10. So you can put those outside the circle S. Remember what we call the things outside a circle S? We call that the complement of S. So outside here, we've got all of these numbers which are in the complement of S, S dash. Anyway, let's move on now to an example, another example here. And this is pretty much the last example for today. Actually, I'm going to zoom in so you can't see the answers. Or actually, I'm going to scroll up so you can't see the answers. Okay, here, the universal set U is 0, 1, 2, 3, 4, 5, 6, 7. And then we also are given set E, which is 2, 3, 5, and 7. And now they want us to list the set E dash. Once again, E dash we call the complement, and it's everything outside E. And we also want to illustrate E and E dash on a Venn diagram, firstly. So let's start by doing that. So I'll draw my little Venn diagram, although you and I both know that the answers are further down on this page, but I'm not going to reveal them until we do this on our own. So this is going to be our E. The whole rectangle is our U, and everything outside the circle E is going to be E dash. Now, what do we put inside the circle? Well, 2, 3, 5, and 7. So let's go ahead and put those in there. 2, 3, 5, and 7. You can just draw them any way you like. They're just floating in that little circle E, these numbers. Now, what do we put outside? Easy peasy. The numbers we didn't put, the numbers we haven't put in there already. So basically, which ones have we used? 2, 3, 5, and 7. Well, 2, 3, 5, and 7 have been used. Therefore, the ones we haven't used are 0, 1, 4, and 6. That's pretty much it. So we are done with this first bit. List the set. Oh, sorry, I didn't actually list the set E dash. My bad. Let's go ahead and do that. So the list for the set E dash will be all the numbers which are not in E. So those would be 0, 1, 4, and 6. And as you can see, we've got them in the Venn diagram as well, 0, 1, 4, 6. So now we've done all the first bit they asked us to do. Let's move on to the next one. N or V. What does that N represent, guys? Do we remember N or V?
All the numbers inside the set.
Exactly. Thank you. So here, the numbers inside the set E, how many do we have? 1, 2, 3, 4. Easy peasy, lemon squeezy. Moving on to the next one, N of E dash. Now, once again, what does N of E dash mean?
The right hand.
Exactly. The number of elements inside E dash, which is everything outside that little circle E. So how many do we have there? 1, 2, 3, 4. So that is 4, and we are done. And last but not least, what is n of u? It is 8. Excellent. So I thought we would have at least one student who would fall into a trap here by saying, oh, look at u. It's the numbers between 0 and 7. So we have 7 numbers. Quack, quack, quack. You missed the 0. So keep that in mind when you got an extra 0 there. Count the 0 as well. So you got 8 numbers there. So n of u is all the numbers we have been given in this question. So it's actually equal to 8 because there's 8 numbers in u. And that is the way the cookie crumbles. What is this strange looking thing actually? This is a representation of the natural numbers, the whole numbers, the integers, rational numbers, and real numbers. So let me explain what we have here. Remember we said that the natural numbers are the numbers 0, 1, 2, 3, etc. So like positive whole numbers in a way. Then we said Z are the integers, which are whole numbers, which means it's like everything in the negatives, -3, -2, -1, 0, and then the positives 1, 2, 3, etc. Then we said Q is rational numbers, so it's Z plus together all fractions and decimals, which we can make using whole numbers. This is not 100% correct the way I'm writing it, but I hope this is going to help us remember what this Q means. Then we have a thing which we don't tend to use a notation for, but I am going to use a notation here. Q dash. So this is the irrational numbers. So irrational numbers are basically numbers which are not rational. Now, classic numbers here would be the square root of 2, the square root of 3, not the square root of 4, because the square root of 4 is equal to 2. So it's not irrational, it's actually rational, it's a whole number. But the square root of 5, the square root of 7, the square root of 8, what about the square root of 9? No. 3, exactly. Square root of 10, and we can just carry on forever. Pi would be another irrational number as an example. And then I could just come up with one, 0.123757212, and just carry on forever with no particular order. That would be irrational. So what are irrational numbers? Numbers which just are decimals which never end, and they have no pattern, no specific pattern. This is never end. So try to imagine one, and then your brain will explode. That is an irrational number, okay? Whereas rational numbers, we can imagine they are fractions. Right, and we saw some things here. We had a bit of an issue at some point with a quiz. Here, this also includes recurring decimals. So in rational numbers, we have this thing with recurring decimals. So it's the only kind of infinite decimals which never end, which are actually rational numbers. Because, for example, you would have 1/3, which is 0.3333, carries on forever. But that is rational. It's not irrational. And then finally, real numbers. The real numbers are basically all numbers that we have seen thus far. So any number of the above, out of these above numbers, will be a real number. Okay.
Sir, can I ask you something?
Yes, by all means.
The n is the 16, the z is the -2, and the n, the q is the z 8.5, 0.115, and 7.1, and the r is the q and the square root of 3, right?
R is the square root of 3.
Okay, now I understand.
Yes, and this is actually Q because it's an ending decimal, a decimal which ends. Yeah, so you can write it down, for example, as 115 over 1000. So it is a rational number. But yes, this is basically what just saying 8.5 would basically be written as 17 over 2 if you put it as a fraction. So if you can write something as a fraction, it's a rational number. If it's a negative whole number, it's an integer. If it's a positive whole number, it's a natural number. If it's a decimal which ends, you can write it down as 71 over 10, for example. So that is rational. And then if it's none of these things, like the square root of 3, this would be a real number. So this you might be asked to do, and you might be asked to put all of this stuff into a Venn diagram. You see this lonely root 3, poor thing. This is an irrational number. No one likes it. We don't want to hang out with it, so we put it out here with the irrational numbers, okay? All right, anyway, this is the idea with a Venn diagram, which includes all of these fancy sets we've talked about. And then here, the final example given in the textbook is basically one where you have 2 circles. So it's double the action, triple the excitement. So here we've got the set U, which is the universal set. It's all numbers such that those numbers are between 0 and 12, including 0, including 12 because of these lines underneath. And then this x belongs to z means x is an element of the integers. So let me just say here, these guys are called integers. Okay, so basically our set U is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, that was fast. And then A is 2, 3, 5, 7, 11. B is 1, 3, 6, 7, 8. So how do we put all of this stuff into a Venn diagram? Well, firstly, you draw the 2 circles. So let me show you how you draw 2 circles. This is probably a very important life skill, guys. Remember, you need to learn how to draw circles in your lives. Okay, there you go. That's a circle. Then we draw another one. Let me show you, just so you don't get confused. So this is a circle. Great. And then what do we put in the middle? We start with the middle always. We put the thing...
We put the numbers that are in both.
Excellent. Somebody spoke exactly, said exactly what I wanted to say. Brilliant. So 3 and 7, they are the numbers that these 2 sets have in common. So we'll put the 3 and the 7 in there, and we are done with the intersection of the 2 sets. Brilliant. Now let's move on to the leftovers of circle A. Since we took already the 3 and the 7, let's go and put the rest of the stuff in the rest of the circle. So 2, 5, and 11 will go in here. 2, 5, and 11. Done. Let's move on to set B. Since we already used 3 and 7 and they went in there, then we've got the 1, the 6, and the 8, which need to go in here. 1, 6, 8, and we are done. And most students here would say, whew, finished. Venn diagram is complete.
The numbers that aren't in the Venn diagram outside.
Yes, exactly. That's absolutely right. Now we need to put in the rest of the numbers here, because remember we said these are the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we've already used these numbers, so we have to figure out which ones we haven't used yet. You need to come up with your own trick here, but anyway, it's easy to see that the remaining numbers would be 4, 12, 10, and 9. And we put them outside the circles. No one wants to hang out with those numbers. We'll just put them out there. And that's pretty much it. That's how you complete a Venn diagram with 2 circles, A and B. I'm going to stop the recording here, and obviously I'm going to be here, and I'm going to be helping you if you get stuck on anything on dudes.